Hello, everyone, and welcome back. I'm Jack Rincon here with Dr. Pei Pei Peng, and we're excited to continue our Bridge to AI Training Working Group lecture series for 2025 and 2026 as part of our Novel AI Technology module. Today's session is titled From Volume to Value, Rethinking Data for AI in Health. This is a particularly timely conversation as we collectively grapple with what it truly means to build reliable, high-impact AI systems in biomedicine. Dr. Ping?
Thank you, Jack. It's our honor to welcome today's speaker, Professor and Vice Dean at the Aaron Fulton Schools of Engineering at Arizona State University, Dr. Teresa Wu. Professor Wu is also the founding director of the ASU Mayo Center for Innovative Imaging. This has been shown as a powerful collaboration, uniting both engineers and data scientists with clinicians at Mayo Clinic to advance data science-driven projects and programs for clinical medicine. Professor Wu's work focuses on machine learning and deep learning for heterogeneous multi-modal medical data with unique applications spanning aging, disease, diagnosis, and prognosis. We're so delighted to have her guide us through how we might rethink data foundations in health AI today. A little bit more about the accomplishments of Professor Wu. She truly is a distinguished scientist in healthcare systems at the cutting edge of integration of engineering and AI-driven medical innovation. She has led major interdisciplinary initiatives bridging engineering and clinical practice. Her work has been recognized through national honors, multiple NSF CAREER Awards, and other important recognitions. And she has also served in influential editorial leadership roles across engineering and healthcare. Again, we're truly honored to have you join us, Professor Wu, and I'm handing it over back to Jack to manage the learning objectives.
Thank you, Pepe. So in today's session, we will focus on three key learning objectives. First, we'll review the evolution of AI methodologies, particularly in quantitative medical imaging, and examine how modeling approaches have changed as data environments have grown more complex. Second, we'll explore a critical and often overlooked question on how data quality versus data quantity influences model performance, reliability, and ultimately clinical trust. This discussion is especially important as large-scale data collection becomes increasingly feasible, but not always strategically structured. Finally, we'll learn how post-hoc collaboration techniques can improve predictive performance by attaching meaningful measures of confidence to AI outputs, a crucial step towards deploying models responsibly in real-world healthcare environments. And with that, I'll turn it over to Dr. Wu so she can take us from volume to value.
Let me know you can see the share screen.
Yep, looks good. Thank you.
Thank you very much. Thanks, Pepe. Thanks, Jack. The honor is on my side. So today we're going to talk something about the volume to value, so from V to V. And we got to think, because these days people are doing a lot of work in terms of foundation models. So that's led me to think about, shall we really thinking about the more the better? Would that really have any impact from the data qualities? So that's where I'm going to start today's conversation, to share some of the things we learn, some of the things we do here. I'm a professor from School of Computing and Augmented Intelligence. I started my very first collaboration with Mayo Clinic back in 2008. So over the last 18 years, we've done a lot of very interesting work, and that's also support some of the talk today. Next, so this is routine. There's no relevant disclosures, and I will just go to the next slides. As one product from the collaboration with Mayo Clinic, 10 years after the first collaboration with Mayo Clinic, we have this center established in place. Our collaborators really from Mayo Clinic, different departments span through radiology first, and later on, we have faculty from oncology and faculty from neurology, those departments join on board. From ASU side, we do see the healthcare systems. That will be industrial engineering. We have ECE faculty doing the imaging processing. We also have faculty from bioinformatics, faculty from computer science. So I will just say it's truly interdisciplinary centers. What we want to see is, can we find the synergies? Let's just break the boundaries of the discipline, not only within the engineering, also break the boundary between engineering and the medicine. Let's just bridge them. I think that's also the title of your center is Bridge AI. We can using data, we can using knowledge to bridge, get people together, solve this impactful problem. That's sort of like the motivation we have this center in place. So in this case, we want to solve this impactful problem. And basically, we are having this categorized into 5 different domains. We look at the care, we look at the monitor of the health, proactive, and we do the diagnosis and prognosis, predictive, and eventually treatments. So if you look at this ring, and zoom in, you will see they are all kind of different type of data here. We use the EHR data using the diagnostic imaging, genomics, personalized, and remote sensing, smart sensing. And what we are trying to get, if you see zooming in and in and in the middle part, that's the individual has the big data. It's kind of interesting how you see the big data, how you see the individual. And if you look at the bottom of this slide, the message we try to deliver here is precision medicine. So what that means is really, in my view, is N to 1 problem. What I mean N here is you are collecting cohorts, large populations, large data in terms of sample size. If you have a large cohort, large sample size, and in the end, the true impact is really getting to the individual. So that's what we mean, the precision medicine. We need to make sure for that individual, you need to customize the solution, make sure you are proposing the correct, the right decisions to the right person at the right time. So in that case, on one dimension, we are seeing we have a data volume is large. We have the data, it's coming from different sources. And in the end, we want to see the impact from N really driving into the decision on the one. So if this is the case, we see the data science research in the patient care domain. We have volume, we have quality, we have N, the samples, we have the Y, individuals. And next, I'm going to just revisit. First, the learning objective today, just say what are the research AI methodologies. And I'm going to use some of the examples from my centers to illustrate those AI methodologies. And that will lead to the second objective, which is quality, quantity, and the last one is more like a calibration post hoc. In terms of reviews, people keep thinking, okay, we look into the stories is becoming larger. Volume, computational platforms support larger. Algorithm support larger. So the model is becoming large, the data is becoming large, and we have a lot of computational powers need to consume to support this exciting research domain. And we just have this put in this time horizons. If you look at the y-axis from the top to down, that's what we see, all the changes. And today we're going to focus a little bit this is southeast corner. And in that case, that's in the medicine from traditional machine learning. You can see back in 2012, using the traditional machine learning, focus on the handcrafted features. At that time, thinking about imaging is more like given the imaging, we have radiologists going to draw the ROIs. And given the ROIs, we have some pipeline in place to extract handcrafted features. Those usually text features. So they are different text feature pipelines to extract that. With those features, you can develop some machine learning, okay, to do the supervised and supervised approach. Later on, it's becoming more the deep learning. In terms of the deep learning, at beginning, there are at least two different ways to use deep learning. One is people are using deep learning as a way to extract the feature. That's a way, and then some hybrid approach proposed using this extracted feature from the deep learnings, build some classifiers. That's a hybrid machine learning, deep learning approach. And further, people start doing the deep learning as end to end. If I'm giving you the imagings, go to the deep learnings, and I'm just in the end going to do predictions, classifications. So that's sort of like almost 15 years ago. And later on, people say, we do this N-to-1 things. When you have a large cohort apply for the individuals, often the data set you collect local. In my collaboration, we have the data collect from Mayo Clinic. So if I am using the data set, trained some other models, can we using those models? How generalized those models are can be used to the data we collect from Mayo Clinic or WashU or Banner or Barrow. Those are the examples. That's where researchers start looking into the generalizations. We hit some troubles, we hit some bottlenecks, and that's transfer learnings coming into the picture. It's possible we use some model to build this pre-trained model, and we do some sort of transfer learning. Those models can be applied to the local data sets. That's sort of about 10 years ago. And later on, people say, in terms of the data, there are some issues. Can we look into, instead of descriptive models, what is the advantage we can really take from the generative models? Or can we look into some self-supervised learning approach? And that's sort of like around 2018, 2019-ish. And the last one I'm showing here is people looking into foundation model. And foundation models, there are different type of foundation model. Another thing I listed here is number 5 is, before the foundation model is vision language. When you say vision language, it already gives you some hint. We are looking at a multi-heterogeneous data using really multi-modal data to handle this. So this is the evolution of computing. And in the meantime, we say vision language model, foundation model. We are also supporting the algorithm to handle data with the growing volume. That means we do see the trends. I'm going to quickly present it here. Currently in my lab, we have the access to the UK Biobank. We also leverage the data collect from all of us. So there are different sources of data, and some of them focus on imaging. They do have genomics. They do have some wearable sensors. They do have some surveys. So those data can be certainly leveraged to support these N-to-1 problems. And next slide is just some example of foundation models. You will see the foundation model is built at different domains. For the medicine, we use biomedical, which is imaging and the text together. We also using the SCGPT, looking into the genomics. here just give you an overview. What are the things existing in the field? You can see foundation model is really booming. So as we are working on something in the genomics for the AD studies, just last year from 2024 and 2025, we already have 4 papers published on foundation models in genomics in the Nature families. So this is a very popular areas people should focus. As I mentioned, I give an overview in terms of the hardware, the data, the software algorithm, existing models. And next, I think maybe it's a good idea for me just to talk some of the examples to give you some ideas what is being done in terms of the data. So this is look at this 5 categories. The first one is the care. Our very earlier work, as I mentioned, started with Mayo Clinic 2008. We're really looking into the care coordination. We're looking into the quality of the care, focusing on radiology. So in this case, we look at the radiology, we have a large system developed called the dose index tracking system. This system right now is being used in more than 20 hospitals within the Mayo enterprise. So this system was earlier work, really looking into how can we collect some data, looking into the quality to have the real-time alert if there are some issues, to have some alarm trigger for the radiologist and the technologist. Further, we're looking into that to do the care coordinations. Can we using this to help the scheduling of scanners, also coordinate with other departments within the hospitals. So that's sort of the earlier work we did in terms of the care. So what we can see at that time, it's pretty the sample size, number of subjects is pretty large. Relative feature size is relatively narrow. Next, we move to monitoring. That's what we are doing even now these days. We look into the Alzheimer disease, looking into the data using imaging, looking into the data like the walking, the sensors. We are right now working into have this Doppler radar sensor to monitor the gait because it's known the gait is a good biomarkers indicating the risk for the individuals developing the Alzheimer's disease 10 years before this symptom occurs. So in that case, it's a very good early biomarkers. We are looking into the study monitoring, we are looking into the sensing, and because you have the sensors installed at home, you have to look into some sort of effective learnings if you want to scale doing this in communities. And that's, we have more work indeed to focus on really the diagnosis part. For the imaging diagnosis, we do a lot of migraine classification, concussion classification. We're using the imaging data, which is multi-modal imaging, including multi-protocol imaging, MRIs, CTs. For the MRI, we have T1 imaging, T2 imaging, and DTI, etc. So how are we going to really take advantage of the imaging data to build a robust model to do this migraineurs classification? Meaning some of the migraineurs, they probably going to be very consistent, that's chronic. Some of them may be just episodic. So how do we really have a better classification accurate for this problem that following the diagnosis? Also, we have some other things working on for the breast imaging. For the breast imaging, we're using the deep learning, transfer learning, and indeed later on, we start to do some generative AIs in this domain. For the Alzheimer's disease, this is something we are going on using the imaging. We know for the AD study, people know MRI, good, structure, PET, good, functional. So if we have MRI, PET imaging, have them fused together. That probably will be even more powerful than using any individual modality imaging alone. We hope all the patients, they have both modality available. Unfortunately, that's just the hope. It could be true. So in that case, it comes to this missing imaging modality problem. Early days, people handle this on the feature space. It's like early days when people using handcrafted features, they could using some statistical imputations to just impute the features to get this missing piece filled in. And our team started 2018, 2019-ish. We said, can we looking into the imaging to imaging translation? That's where we started the first piece of work. It was a model called RIED. It's imaging voxel to voxel level translations. And that's supervised. Later on, we get into more and more Gen AI, unsupervised, using some of the GAN models to render a synthetic imaging of one modality given another modality. And this can be used not only the MRI, CT, or PET imaging also. One of the ongoing projects we have right now is looking to PET imaging, tracer harmonization. Means if I have PET imaging from PIB, it's one tracer. We have PET imaging from FBP. They look visually quite different. In that case, it's really hard to make a good diagnosis cutoff. If you're doing any study across the center nationwide, they are using different tracer, it's hard to reach the consensus regarding the diagnosis criteria. What can we do? If we are able to using AI, using Gen AI specifically to do the harmonizations, that can address this problem. Next, I do have a couple more slides. I think given the time, I will try to speed up a little bit. We have some work in terms of prognosis. In this case, we're looking to really specifically challenging task is the subtypings for the TBIs and also the PTH. For the PTH headache subjects, we want to see some of them acute, some of them really persistent. And how do we really do the subtypings? We are using some models. Initially was very sparse learning, and later on we are getting more and more a generative model and a foundation model approach. And the treatment, we are looking into some toxicities, and some initial work was more like radiogenomics. That means have the imaging, which is macro level, and the genomics from the biopsies, and how do we have some correlation established? That was the earlier work, and this is still continue working on. So that's sort of like following this ring with 5 different areas. Additionally, I just want to have one more slide added here in terms of foundation models. Okay, so we are working on foundation model. One type of foundation model was using the biomed clip. I want to mention biomed clip. It's really because this is initially it's pretty large, using 15 million pairs of the imaging and the text. I want to share this piece of work. So we use this biomed clip. We know using foundation model should be powerful. Foundation model is built using very large volume data, could compensate some variations of the data from different sources. And for biomed clip, we specifically interested in this because it's not just foundation model on single modalities. It integrated the data from text as well. Thinking about the medical applications, we have the imaging, we have the radiology report, we have the EHR, we have some other notes. If there's a way, we have them all integrate together, fuse them together, fuse them optimally. That can really probably address this N-to-1 challenge. That was the initial hypothesis. We want to try it out. We have some earlier work published in the brain communication, purely using the imaging alone. We built this self-supervised model, have some good results. And we want to see if we are leverage foundation model, can we get a better result? The challenge we see over there is for this specific data set, we want to compare apple to apple using the same data set. Unfortunately, we have the imaging, we do not have the complete, the text data from the EHR from radiology report. So some of my students try to say, let's do some prompt engineering. If we are able to generate some prompts, give some prompts, generate the text, maybe using that, we will have this biomed clip. The two hats, one is the text encoder, one is the imaging encoder, have these two hats complete. We tried it. And when we see the results was too good to be true, we say, why so? We look at the prompt engineer, it's biased. We just cannot trust. So that gave us some headache. Say, if this is the challenge, a purely prompt engineer brings some issues, what can we do next? Then I said, let's just try out only one leg. Instead of have two legs walking in parallel, let's just focus on the imaging headers. See if I'm using the imaging headers, can we get something interesting or not? Fortunately, we did find using the imaging encoder pre-trained from the biomed clip, indeed, does give us an improved performance compared to our earlier published work in the brain communication. So what that tells me? That tells us, we're still testing this hypothesis, that tells us biomed clip alone is trained by using two sources of data, text plus imaging. And indeed, because this pre-trained process, it's already leveraged the rich information from the text. So in that case, the imaging encoder alone already being empowered, taking advantage some of the text information from another header. And if you're using that to do the following tasks as encoder to generate the embeddings, maybe you will get some surprising results. So that's what we find from this biomed clip study. And on the left-hand side, this is another study we are working on is purely using the imaging because the Dino V2 is imaging foundation model. Unfortunately, it's only just 2D slice. So we have to look into how can we handle the 3D information using this foundation model to really extract the embeddings, which give us the informations, not ignoring the spatial relationships. So that's some other things we do. We have some presentations in the ICCV workshop just last year. So that's sort of like give an overview about the AI methodology, changing from the initial handcrafted space to end-to-end deep learning and look into generalizations, get into transfer learning. And then people are looking into how can we using generative AIs. The one I presented earlier, really looking into using GAI, generative AI, to do the data harmonizations. And there are a lot of people also using generative AI to handle the data augmentation. Why they want to handle the data augmentation? Because in the medical field, the data size, most of them local data set is small. And fortunately, people already looking into that. People start to accumulate more and more data. That's the large data set, and the larger data set from those big initiatives from UK Biobank, from all of us, and the others like TCGA for the cancers. So the data sets start to accumulate. We're also using another public data set, Fitbird, across multiple centers. So those are starting to appear. We get pretty good number of initiatives try to collect large amount of data. We have data available. We are able to look into the large model. If we're able to build the large model, we could using contrastive learning or other ways to build foundation model. What does a foundation model mean? As this name here, foundation model means to as the basic foundations to provide information for the following tasks. You can do classification, do diagnosis, do prognosis, to do the treatment planning, to do the care coordinations. You can do all those following tasks, and we can certainly using this foundation model to support you. For example, extract the embeddings or extract the features to finish those tasks. When I look at this, I had the questions in my head. In my mind, I said, quantity is growing, enable this. Shall we look at this problem from another angle? That is the quality. So how does the data quality play a role? Can we say if we are much enhanced the quality, maybe we do not have this high demand of quantity? That is the hypothesis drive me into the research, which is the second learning objectives. Indeed, it's kind of very interesting this morning. We have a paper submitted to AI in medicine. We just got the feedback this morning, have a minor revision. So this piece of work is very timely, tied to that paper we just received the review. So this part, we want to look into the quality versus quantities on the performance of AI model medical application. Take a look at this. For illustration, I put a little bit of animation on the right-hand side. We know the data is noisy. Maybe the data is coming from different scanners. You have MRI scanners from Siemens, from Philips. In this case, there is a little bit difference from the equipment. There will be a little bit different, not only the equipments, but also the software processing, different version of that. And from the human, if you are getting the abdominal imagings, quite often you have the motion, but also for the head, you can see imaging is blur. So in this case, you have some of the data pretty noisy. And if you look at this animations, I'm trying to show on this right-hand side, we have healthy and the diseased subjects. If I am suppose the true decision boundaries will be this way, and because of the data have some issues, and indeed this is building the classifiers for illustration, you will see it's deviated from the true boundaries. That is some issues from the noisy data. And another challenge in terms of the data is the insufficient labelings. So here is one example we show at the bottom. This is one of the projects we work on is for the kidney using MRIs. The whole hypothesis here is in the kidney imaging, we are able to use using this imaging derived biomarkers like a glomeruli. So we want to know the number of glomeruli and the size of the glomeruli, the distribution of those. Those could be a good biomarkers indicating the stage of the kidney. And in that case, we can quantify this to make the transplantation decisions. For example, it's quite possible you have a 45 years old kidney, another is 60 years of the kidneys. Well, Okay, if you can quantify that, you know the healthy stage of the kidneys to make the decisions. However, for any human beings, look at the MR images, you will see each human kidneys, we have over 1,000,000 glomeruli. In that case, if you are doing the annotations of those glomeruli to support these models, it's just impossible. And that's very labor intensive. So that's just one example. I showed this insufficient labeling efforts. And again, if we say this is the true boundaries, we do not have the information, you can see this decision boundaries is tilted the other ways. That's another challenge we see. Here is a challenge just from the examples we show here is the patient subtypes. I mentioned a little bit earlier, we could have the migraine subjects. We could have headache subjects, some of them acute, some of them persistent, so recovered or not recovered. We have the migraine, which have, without aura or with. We have episodic or chronic. So all those things really blending together make even looking to the disease cohorts, they are different subtypes, and that makes it pretty challenging to look into this. So if we have the data, now we are getting into the issues let's just go to this. We have the data unlabeled or insufficient label. Some data have noise, and some of the data you are really looking to the patient subtypes have a different heterogeneities in this case. We are looking into such data. How do we handle the data? The more the better might not be. You need to look into how do I really improve the quality, and that will support a better modeling. So we do want to acknowledge, I add one line at the bottom here. We do want to acknowledge currently there are a lot of effort, especially in the imaging domain. We look into data curation, we look into data harmonizations. That's where generative AI play a significant role here, okay? But what I am trying to present today is another idea. So what we are trying to come up the idea, we call this healthy core. What does that mean? It's really came from one of the conversations I had with my neurology collaborators. So he said when they are really doing some clinical trial studies, they recruit always, it's a normative model. Not normative models, you always have control group, and then you have the intervention group. In one of the studies, we try to work together. We have 3 different data sets. One data set collected from Wolff U, 2 data sets collected from Mayo Clinic at different time frames, probably 5 or 8 years apart. So we try to test the generalizations of the models. We hit a lot of roadblocks. And that's where we say, okay, is there something we can really look deep into this? One conversations we had in one of the coffee hours was how confident they are, the clinicians are, when they are recruiting the healthy controls. The healthy control may have some heterogeneities as well. So that motivates us to think about this concept. We call this healthy core. I mentioned about the normative model. As also, I used the example. I said, when we want to monitoring individual, taking an early example I had about the gait telemonitoring. If I have a sensor installed at home, I can monitoring the gait, and I can see the risk of that individuals, the fall risk and the risk to develop AD or dementias a few years down the road. When we monitoring that, we got to build a baseline of that individual and see if it deviated from this baseline. Again, that's the concept of normative. Then I just discussed this. I said, for me, If I am having a breakfast in the morning, then coffee, then my symptoms, all those biosensors collected, the biometrics will be different. For me, I get up at the same time. However, I rush to school. I did not have my breakfast at all. And I drink tons of coffee that day to make sure I'm awake. So in that case, the normative models, the baseline you are building will be problematic to take the same time frame, 8 to 9 o'clock, that time frame to build that. So in this case, maybe when you're collecting the data, time series, or even the cohort subjects, we need to look into a little bit of variations, the variation of the individual over the time, or the variations across the subject within the cohort. And that is the idea. So we want to see if this is the case. Let's look at this cohorts. We need to really get the healthy cohort, and we call them core. If I'm using this core concept, that probably can help solve some problems. And this is what we do. Basically, we say if this is the true boundaries and there are some other cases, we have this cross to cross, okay? We call this borderline case. I will show that in the next slides. If we're able to identify those borderline cases, remove those borderline cases, the model might perform better. This is what we were hoping for, and this is what we try to do, see if it is the case. So what we do here is we have the healthy cohorts. For the healthy cohort, we know we can have them separated, which is the core, the one really we love the most, and some borderline cases, okay? And the whole hypothesis here is the borderline cases and all the healthy cases, they will not have the same shared centroid. That's why we call this borderline cases. And based on such assumption, we will know the KL divergence from the PB, this PA, should be less than the PC or PA. The P is really the probability, the feature distributions given those feature space. The C is the core, A is the diseased cohort, B is the borderline within this healthy cohort, and we know B plus C is overall healthy cohort. So if we know such assumption, assume, right? So that's really intuitively hold, meaning the borderline is less separable compared to core against the healthy, the disease subject. Based on this, we have some proof on this right-hand side, and the conclusion we are seeing here is if we focus on the core, that provide us the lower bound for the KL divergence. And if that's the case, we're able to do a better separations. Next question. Assume this is good. How do we really get who are the ones I need to include in my healthy core? The basic idea here is we have is high dimension. Let's go with the PCA. So have this reduced to dimension, remove some noise. So that is the first step. We do this PCA projections. Based on the PCA, assume we have multiple components, the principal components, we're going to do the selections. What we do here is we're using this bootstrap approach, and based on the bootstrap, for each sample, we're going to calculate the KDE. KDE is kernel density estimation, give us some ideas. Based on this KDE value of any samples we bootstrapped, we're going to have them ranked. And following these rankings, we're going to run multiple times. We will see the overlap, those overlap indicating what is called core stabilities. And from this, we're going to really identify what are the cores given this sample. Remember, core is a subset of the healthy cohorts. Once we identify this, we're going to train based on this core subset versus diseased sample. Okay, so one thing we do is let's evaluate on all the data sets. Okay, in that case, all the testing data set, that means we have the disease sample, all of them, and not only the core, but all the healthy sample initially provided in the original data set. The second experiment we want to see is let's evaluate the performance on the healthy core only plus the disease of the samples. This is the thing we did. We try a number of experiments. The first data set roughly have the first two data sets, the public data sets. So the first one have roughly about 8,000 samples. It's half-half. And you can see, let's focus on the first two rows because the next two experiments have similar pattern. If you focus on first two rows, you will see if I am using the full training testing, or I'm using the HC only to do the trainings, and I do the HC testings, and I using the HC trainings on the full testings, and you will see the results is showing quite interesting in terms of the second row compared to the first, the significant improvements that is as expected. Why? Because our central hypothesis is in the healthy cohorts, there are some cases, those cases becoming a little bit heterogeneous in these data sets give us some question mark. How valid we treat them as healthy? Or should this borderline, if they are borderline, how close they are to the healthy or how close they are to the other side of the aisle? And in that case, if we have those find out, we find this a purer course, the results should be much improved. So this is what we do in terms of the healthy core. And we said that interestingly, instead of purely looking to increase the volume of the data, we are not harmonizing, curate the data in the sense we are not augmenting. We are using existing data set, and we try to really find a core reference using that could be good. And next thing I'm going to talk very quickly is something we are working on right now. This is also coming from the first learning objective. The first learning objective we take away is we get a lot of ongoing work into this foundation model dimensions. If I have foundation model, what do I do? You can see quite a lot of ongoing work is treating the foundation model as a way to extract some embeddings for the subsequent task. And most of people really using foundation model, first of all, do a little bit fine tuning given any local data set. See if I have 200 subjects collected from Mayo Clinic or from other clinics. So the size is small. One thing people sometimes do is, given the foundation models, I do a little bit fine tuning. And after I have this fine tuning, I apply to this local data set. That's the approach. And what we are thinking is, instead of doing these pre-steps, can we do something to the post-step? This is what we have, this idea called the post-hoc calibration. Why we are interested in this post-hoc calibrations? We know for any looking to classification, when you have any classifier, the output from your classifier indeed is a probability. So the probability goes to top, lower, or the mid, which is quite uncertain. So in this case, there is some cutoff going to assign which class this belongs to. But if you look at these probabilities, there is something interesting you want to further explore. So if this is probabilities, it's indicating how confident you are regarding that specific one instance, get you up, down, or unsure. And a lot of people really look into this probability calibrations. And in this case, so if they are calibrate this confidence, then that means you're going to have a higher confidence to have this assigned to the right groups, the right clubs. That's what we do. And number of classic method, existing approach, using some different scaling approach, using Dirichlet calibrations. And they are using this calibration really simply looking to the post hoc calibration, the same meanings we are trying to accomplish here. And they all sample dependent. Some other existing approach, I have this list over here. So in this case, what we are trying to look into is most existing approach. Most existing approach, they focus on the MU, the first components in this logic. This is what the classifier built upon. So in this case, we said, instead of the principal, the classifier all based on these dimensions. Instead of the principal dimension, there is other dimensions. It's more like a residual. Will this residual play a role in this post hoc calibration or not? And that was our interesting question stem too. So what we are doing here is, if you look at the slides, we have any given the data sets, we have a principal, that's the primary directions, and the principal primary directions versus others. The others, if we have a dimension space of n, the principal is the one, the other dimensions will be n minus 1. And we are interested to explore how this n minus 1 dimensions play a role in this calibration. And we have some proposed approach here, focus on this n minus 1. We're using the bin approach. We derived some regressions of each of the bin, and we're using this to approximate, using these approximations, get to the second component, the second term. The second term is really the orthogonal evidence. That means the primary and all others. That's the orthogonal evidence. If we have this orthogonal evidence coming from all others, we are hoping this logic will be better capture the confidence of the data predictions. To test our hypothesis, we first did some simulations and to provide some visuals. As you can see, what we did is this is the northwest corner. Northwest corner is the true posterior about this distributions. Based on this is given this, we generate this northeast. So we threw a lot of dots, a lot of samples based on such distribution. We generate a lot of samples. And given these samples, we just fit a classifiers, and that's how it looks like. This is southwest corner, like Arizona. And this is the right, this part is southeast corner. You will see after we do this post hoc calibration, adding that a second term, which is orthogonal components, you will see, compare these two diagonals, you will see the distribution looks very similar now, get return. But if you look at this Arizona here, you will see the background's distribution is quite different from this northwest. So that's just a visual to show. We run a number of experiments, and I will just quickly show you using some metrics. I will just quickly show, indeed, so far this result showing it very promising, indicating the advantage of using this post hoc calibration. So for the time being, this is the same exactly, but using the different data set on the imaging and running the deep learning models. Again, the conclusion holds the same as the early one. And that will conclude the third takeaways. So if I have foundation model, instead of looking into fine tunings, another way to do this, probably I want to improve the confidence post hoc calibrations, and that can directly use some small data sets. That's sort of like a conclude the overall. I think I have roughly 4 minutes instead of 14 minutes, as Jack hopeful.
Yeah, thank you. That was a lively talk. Thank you, Dr. Wu. At this point, we would open the floor for questions. I think I may see a question. Let me see. The first one I see here is actually, Dr. Wei, would you like to help out with questions or should I take over? I'm not sure what we're going to do.
I'm happy to facilitate that. So the first question, I mean, by the way, this was a wonderful talk. I enjoyed it. So, in light of time, maybe we can only have very quick answer and very brief answers. So I wasn't sure. The first one, probably a comment, not a question. And it's basically the value in healthcare AI, right? So it's far exceeding the volumes of data, which I completely agree. And the second one is a question from Stephen with respect to the homogeneous healthy core. What are some ways one can determine which physiological features are most relevant to start with when creating the dense score? Would these features be selected for a specific disease or selected for more general cases?
The first comment from Randy, I think that's very valid that we do. So look into diversities. We are AI models. Another thing we do is look into the fairness. So you have to remove the bias into the models. That's a very big thing. Regarding Steve's questions, Steven, so what we do here is we use the principal components. So in that case, you can think about it as just a linear combination of all the features. We are not selecting which features to be included in the core selections. Instead, we use the PCA to support. We can certainly having the PCA mapping back to those features and see what are the features carrying heavier coefficient, which is really playing more weights in this core selection. I hope I answered the question.
Yes, thank you.
Yeah.
I
There is
think we
one last
don't.
question.
Yes, go ahead.
He goes, since clinical distributions shift over time, how often would recalibration post hoc need to happen? And at what point does frequent recalibration begin to mask underlying structural model decay?
You are talking about the post hoc calibrations?
Yeah. Do you think there's, I guess the question is trying to ask if there's a chance that recalibration post hoc over time might mask underlying structural model decay?
That's a very good, valid questions. I don't think I have a good answer right now. The way we see it, it's really you look into the residual. So when the residuals is really showing the patterns that indicating it adding the value. If it's not really adding the value in the calibrations, in that case, that's where you could just stop.
Okay.
So in that case, what we really look into is really the second terms, how much it contributes here, right? And that's got to the earlier in terms of the regression bin size. I know I went through this very quick. So this is all a serious action is going to really decide. So the idea here is, I think the story I'm trying to tell here is given the foundation models, right? So instead of I'm doing this in the fine tuning, especially we want to explore the applicability of foundation model in relatively local data set, which often small. So this might be just another alternative we can think about.
Okay. Thank you. Dr. Ping?
Jack, we have one more question. I
Oh.
think it's a very important one.
I noticed that during evaluation, when training on the core patients and full data sets, performance drops approximately 20%. When training on the core patients rather than the full cohort, what exactly is the model losing during training that is present in the cohort?
I'm expecting this question. That's why I said pay attention for the first two rows. Remember, one thing is we have just the core patients and the diseased. So the core patient, let's say core patient is 3. I have totally 5 in the healthy, and only 3 of them is the core. So in this case, one case is the 3 and 5, I'm building this training. Another is 5 and 5, I'm building and training. So the losing part is really those 2 problematic borderline cases. But you do see I am being way more confident, the same, to identify those diseased cohorts that keep the same. So that's the confidence we are gaining. And so some questionable cases, those two cases, we don't know. So let's leave that there. Maybe we could ask clinicians to really look into those cases to confirm, are they really healthy or they are really sort of borderline in some sense.
Great answer, Professor Wu. And Ursha, thank you. Very thoughtful question. I want to thank Professor Wu and obviously Jack for hosting this insightful lecture. And I also want to thank Professor Wei Wang for helping us managing all the Q&A sessions here. With that, Jack, back to you for the final words.
Yes, thank you guys for attending, and we really appreciate you showing up. And Dr. Wu, that was an awesome presentation and great answers to the questions. I just would like to announce, please stay tuned. We do have another lecture in March 19th. That's Dr. William Spare from UCLA will be giving a talk on multi-modal deep learning models for thyroid cancer risk stratification. So thank you for dropping by and see you next time.
Thank you.
Yeah, thanks again, Professor Wu. It was not just a great lecture. We learned so much, very insightful. We definitely would reach out to you.
You have my number again.
Okay. All
Let's
right.
talk. Let's
Okay.
be here.
Take care.
Thank you.
Bye-bye.